Hi, well in this video I'm going to explain the Unit 8. Unit 8 it's about magnetism. And here's my guide. Well, I'm going to talk about permanent magnets, about the magnetic force, about the motion of charged particles, magnetic force on wires with current, the torque in a current circuit, the magnetic dipole moment, and the Hall effect. So let's give some background, and this background will start about what's a magnet and where does magnets come from, or how can we know that we have a magnet in front of us. Well, a magnet is basically an object that has some abilities to find fields and direct itself in the direction of these fields that exist. And basically, these magnets are made of of iron oxide. And so what happens is that there's a field, and that's the magnetic field that exists, for example, on Earth. So here we have planet Earth, and that's Mexico. And this planet Earth has an axis here, because actually, if you didn't know that, the planet is not like completely vertical, it's a little bit like inclinated. And here we have a north magnetic pole and a south magnetic pole. If we remember a little bit about current, for example, we have two opposites, the positive charge and the negative charge. Here, and you could have a positive separated from negative, and those would be like charges alone. When we're talking about magnets and objects that are full of magnetic force, they cannot live one without the other. So what I'm trying to say is, if we have a magnet, and it's divided at half, this is the north magnetic pole and the south magnetic pole, and if we leave it like floating in space, like here, it will always try to find the north and the south, like always. And if we try to divide this magnet at half and have now two different pieces, if we were talking about charges and we had a charged side and a uncharged side, if we divided it, then the fully charged side would be separated. But now we have two magnets, because the poles will subdivide and the magnetic force will spread in two different objects. So that's just some background about the permanent magnets, and those are the permanent magnets. So now we want to talk about the magnetic field. So the magnetic field is this space where, if we have this magnet and no, it's the other way around. Oh yeah, so well, the magnetic field lines will always show the motion, like the direction of the magnetic field. So they will always try to go from south to north, like that. So if you think like that, that's very similar. Like that image is very similar to one of a dipole, a charged dipole. Do you remember when we had the positive charge and the negative charge, and the always like the charges that are in the positive try to go through towards the negative one? Well, it's very similar. Now we have the north and the south poles, and they live in the same object, north, south, like that. And well, how do we measure the amount of energy or force that is in this system? Well, that's with the magnetic force. And the magnetic force, well, before that, I want to explain that, thank God, because that's the only reason. When we have two different magnetic fields, and the magnetic field is expressed by a B, and we always have to consider that it's a vector, so it has a direction and a magnitude. If we have one that it's existing like here, that's B1, and then we have another one bigger, B2, and we want to know how do we sum them, or how do we unite them? Well, it's basically a sum. So the B total, or the total magnetic field, will be the sum of B1 times B2. So that's pretty simple, and that's only when they have the same direction, because this is this part. So if we have two, like B1 that's going over there, and then B2 of the same magnitude that's going like to the opposite side, and we sum them, then we have a total magnetic field that is equal to 0. And that's important because that's how they cancel magnetic fields, and they can manage to create some movement of objects. Well, now that we want to measure how many force is in the system, we will introduce magnetic force. The magnetic force is basically the cross product of the magnetic field and the velocity of a charged particle times its charge, well, the magnitude of its charge. So what can we say from that? Like, what does the cross product mean? Well, it basically states that that's the charge magnitude times the velocity times the field times the sine of the angle between the magnetic field and the velocity of the charged particle. So, well, that's the magnetic force, and as we can see, if we have an angle of 90 degrees, so if the velocity is perpendicular to the magnetic field, then we have a maximum magnetic force, and that will be force magnetic, it will be charge, velocity, field, and in case we have that they are perpendicular or anti-perpendicular. Anti-perpendicular is that they're going opposite sides, but like they never touch. Then we have a force B of 0 newtons, and they're newtons because they are a force. And another thing that we can assume from that equation is that if we have a velocity equals 0, so if the particle is not moving, then we have a magnetic force equals to 0 as well. And well, yes, so the force will be directly proportional to the charge the particle has, and directly proportional to the velocity the charge has, and directly proportional to the magnitude of the field. And the field as well will be reducing as the distance increases. Well, but that's another topic that comes with the motion of charged particles. And so if we have a small particle that it's going perpendicular to a magnetic field, so well, I will introduce the right-hand rule later, but now I'm gonna say that we have here, well, this is pointing at you. This is the magnetic field, and this is the velocity of the particle. So they're perpendicular. And once the particle gets close enough to the magnetic field, then the particle will start going like around the magnetic field. And so the motion will be like that, and it will have a constant velocity because the velocity won't change. And that means that it's pointing towards you, and that means that it's pointing inwards. And so now it's pointing towards you. Yeah. And so that's the motion of the particle, that's the velocity of the particle. And so what we can see here is that that's very similar to the circular motion, and we can use the circular motion equations to understand a lot of things. And so I'll erase this a little bit. Remembering here and using the circular motion, we have the force, it's equal to the velocity mass, velocity squared over the radius, and that will be equal to the, and as it is perpendicular, that will be equal to the charge times the velocity times the magnetic field, because that's from the force, like the magnetic force, from the magnetic force. And yeah, and if we try to solve for the radius, for example, we would have that the radius, it's equal to the mass times the velocity over the charge. Well, this is the magnitude of the charge times the field, magnetic field. And this is important because there's something, like some objects, that can separate and identify particles that are going through certain field depending on their mass. And so the mass will define the trajectory of the circle that they make around a field. So this is my field, and this is a particle, and it will start doing this, you know, and it will eventually go like outside the field. It's just like the trajectory that it takes when it gets close to the field. So if we have a small mass then the radius will be small, and if we have a bigger mass, then the radius will be bigger, because the mass is directly proportional to the radius, and that's why it's really important to understand equations like that. So we have like we have the field here, and this is our particle that is charged, and if it's going really fast, then the field will have to apply more force to like change the direction, so the radius will be bigger, and if it's going slower, then it will be easier for the field to change the motion, and it's the same for the mass and for the field and for the charge. If it's more charged, then it will be easier for the field to attract it, and if the field is bigger, well, same thing. And that's important also. And other equations that we can deduce from that are, for example, the period of a circular trajectory. And if we remember, the period is equal to 2 pi radius over velocity. And if we take this and put it over here, then we can see that the period can be also 2 pi mass over charge, that, and that can be also expressed as the frequency, that is 1 over period, and that'll be just that inverted. So we have a charge field over 2 pi mass, and that's another equation that it's important to solve different problems. And we can also use angular frequency, that it's angular velocity, that it's 2 pi frequency. So that will be, if we cancel this and we cancel this, we'll have the magnitude of the charge times the magnetic field over its mass. So that's what I was saying before. The angular velocity will depend a lot on the charge and the field, and it's inversely proportional to the mass, because if we have bigger mass, it will be slower, like the motion will be slower, and if we have a bigger charge or bigger field, then the motion will be faster. That's simple, right? And if now we wanted to, the magnetic force on conductive wire. So we follow the right hand rule. That's like yo-yo-yo. This finger will show us the current, like the direction of the current. This finger over here will show us the magnetic field, and this finger over here will show us the magnetic force. So if we have a current, this is our current, and if we have a wire that has a current that is going like that, and we do the right hand rule, we will know that the magnetic field that is created by that electron flux will go like that. Sorry. Will go. Okay. So yes, magnetic current. The magnetic field will be pointing at you, and the magnetic force will be pointing downwards. Alright? So no matter where you put it, you can always follow the right hand rule. And don't do it with the left hand because everything will go like upside down. And that's an important way to analyze the directions of the currents. So here we have that, and yeah, like that. So we have that the current is going over there, then we do that, and the field is going here, and the magnetic, that's the magnetic force. Alright? As I said before, a dot it's like outside the plane, and a cross would be inside the plane. So what's next? Well, there are some equations that we can use when we're talking about wires. For example, if we use the length of the wire, we could assume that at a certain time t, we would have that the charge is equal to the current times the time, and that if we use that, we could well, also the length it's equal to the to the drift velocity times the time. And well, that's an equation that I don't fully understand, but I'm gonna read it and I'm gonna explain it. Yes, so we have that the charge is then the, what is there? Well, so the charge would be the length over the drift velocity times the current, and if we locate that in our previous equation, and now I'm back, of the magnetic force, we have that L over Vd times I, and that would be Q, times the field, and we're missing something there, and that's the velocity. And we can cancel the drift velocity. Drift velocity is just the velocity of the particles at a certain time. And we can now express that as the force in a length is that. So that's an important equation. We're solving problems with wires. And well, yeah. And then if we're trying to solve, well, now we're using wires, and if we want to analyze how the, as we said before, we have like this, you know, so a lot like a charged particles coming here, and it then turns, and that turn, if we remember a little bit of circular motion, after we saw circular motion, we saw torque, and torque is like a force, but when you have an angle there. So here, if we use a second rule, right hand rule, we will say that we would have current. This would be our current, and this would be our N that we'll later explain. And for that equation, the torque, we have something that it's the current times A times B times sine of theta, and where A is the area and so area, and B is magnetic field, and I is the current of that spiral, and the angle here would be like this angle. And that's an important topic of torque that we will use when we analyze. Because I read this in Spanish, so it's a little bit difficult for me to translate it. But have you seen motors? A motor has bobina. I don't know how to explain it, but if you cover a cylinder with copper, for example, like that, and then you apply a magnetic field over here and a magnetic field over here, then because of the torque, this object will start spinning like that. So if we connect here a receptor of movement that could be a motor, then that movement, that electromagnetic force, can be converted to electrical force, electrical energy. And that's a topic that we will see later about work. And this equation of torque that I just erased is important because you can analyze how much energy you are putting to this system to enable the object to turn. And that's the torque, and that's the importance of torque. And if we now represent that covering the object like that, we would have and as I explained before, and you have a magnetic dipole moment that can be expressed as mu times N times current times area, and where N is the number of times that you go through the object, like around the object. And so this could be 1, 2, 3, 4, 5, 6, 7, 8, and equals 8, and I is a current through the wire that it's around the object, and the area is this area. And then that's a simple way to express to show it. And the torque will now be the mu times B sine of theta. And so torque, it's also mu cross product of B. And so if the if the dipole moment and the magnetic field are aligned, then you have the less potential energy. And if you have that the dipole moment and the magnetic field are like unaligned, then you have the maximum potential energy, and that potential energy can be seen as U theta equals minus mu times B. Times no, that's dot product. And we will now change to the last topic, and this has been an hour of talking. Our last topic is Hall effect, and Hall effect occurs when we have a surface where we have a flux of electrons, and in that surface we have current that it's going this way, current, and then we have a lot of positive particles here, and we drop one negative particle or a series of negative particles at a time, and what it states is that the negative particle will have a drift velocity that it's inversely directional to the direction of the current, and this is BD. That the BD will also have a perpendicular component that's over there, so it will be perpendicular and like opposing to the positive particles, so that the negative charge, that it's basically electrons will go to the other side of the surface. So we will have here an electric field, and that electric field is created because of the Hall effect. And that electric field can be seen as, here we have a distance also. And the battery is dying. And the Hall effect occurs when the FB equals the FE. So when the magnetic field it's equal to the electrical field, and then the Hall effect occurs. And we have an equation that will help us find the magnetic field with that it's B equals change of voltage, Hall voltage, and that's equal to VD times D. And we could have also find the current density, that it's NEBD BD, where N is a number of particles in unit space, unit volume, and that's basically it. It's a very, very, very large topic, and I hope you understand it all. Goodbye.